Induction. An inductor is a circuit element that stores energy in the magnetic field surrounding its current-carrying wires. An inductor is characterized by its inductance, which depends on its geometric properties. In most circumstances, inductors are used in electrical circuits since they store energy in their magnetic field. So what is an inductor? An inductor is a coil of wire that carries a current. This current produces a magnetic field. The energy is stored in the inductor. So basically, an inductor is an ideal solenoid carrying a current I that produces a B field in its interior. Changing current changes B field, changes magnetic flux through the solenoid. Faraday's law shows that there is an EMF generated in the inductor. So the definition of an inductance is the proportionality constant that relates the rate of change of current to the induced EMF. We know that as the rate of change of current increases, the induced EMF increases as well. Also, remember, equation for capacitance, delta Vc equals Q over C. Just like capacitance, inductance is always taken to be a positive quantity. The unit for inductance is Henry, and 1 Henry equals 1 volt second per ampere, named after Joseph Henry, the American physicist and contemporary of Faraday. So the symbol of inductor in a circuit would be something like this. So how do we calculate the inductance? Suppose that a current sets up a magnetic field in an inductor. The B field can be calculated from the size and the shape of the inductor and the distribution of the current. So inductance, which is Li, equals N phi, where phi is the flux, N is the number of turns, I is the current, and L is the inductance. So in other words, inductance may also be defined as the ratio of flux and the current that produces it. All magnetic devices have inductance, but inductance is most often associated with coils. So in a solenoid of length L and cross-sectional area, L over little l, or length per unit length, inductance per unit length, equals mu naught N squared A. Inductance of a toroid is going to be given by this formula. Luckily, we don't have to derive it, we just have to know what this formula is. So there are two basic types of inductances, self-inductance and mutual inductance. Self-inductance is the ratio of the flux produced by a circuit, a conductor, or a coil in itself. The current that produces it usually is denoted by Li. Mutual inductance is the ratio of the flux produced by a circuit I in circuit J and the current in circuit I that produced it, denoted by Mij. Mutual inductance exists between any two circuits as long as there is a magnetic flux or field that couples the two. This coupling could be large, like for a tightly coupled circuit, or small, for a loosely coupled circuit. Energy stored in a magnetic field. There is stored energy in the region around the current carrying wire where B field exists. Two wires carrying currents in the same direction attract each other. If we let the system go, the wires will move towards each other. And we have to do work in keeping these wires separated. This is stored as the potential energy of the system. So for a circuit with an R and an L, basically delta V will be IR from Ohm's law, and delta V will be L di over dt. So in order to form a loop equation, we will do a delta R plus a delta V equals external EMF. That means E of I equals I squared R plus Li di over dt. So what is I and what is EMF or VI? The charge delta Q passes through battery in time delta T. Battery does work on it in the amount E dQ. The rate of doing work will be E dQ dt or di. I squared R is the rate at which the energy is dissipated in the resistor. This energy appears as the internal energy associated with the atomic motion in the resistor. The last thing here is the rate at which the energy is stored in the magnetic field. Since the rest of the energy not dissipated by R must be stored in the magnetic field. If UB is the energy stored in the B field and UB over dt is the rate at which this energy is stored, then the total magnetic energy stored in an inductor will be given by 1/2 Li squared. We don't need to worry about where these formulas are coming from. You guys just need to make sure that you know these formulas for the tests and the quizzes. Energy density, or the energy per unit volume in a magnetic field for an ideal long solenoid, will be given by this formula. U equals 1 over 2 mu naught B squared. Now let's talk about LR circuits. So a circuit consisting of an inductor and a resistor connected in series is called an LR circuit, where S is a switch, E is the external EMF, and R and L. So the general solution for the current through this system will be given by E over R, 1 minus E minus T over tau L, where tau, again, is the time constant. With a battery in the circuit, we can say that as time changes, the potential increases to a maximum potential for the resistor. However, for the inductor, the potential will decrease over time. If next we throw the switch from A to B, remove the battery from the circuit, the current starts to flow. Knowing that T equals 0, the current is I equals I naught E to the minus T over tau. What this will show is for the resistor, the voltage will slowly leak away, and for the inductor, it will be this way. So is there a comparison between an RC and an LR circuit? And the answer is yes. For a capacitor and an inductor, there are some things that are very similar. So the voltage for a capacitor is proportional to the charge. For an inductor, it is proportional to the rate of change of current. For a capacitor, the voltage can change continuously. What can change continuously for a capacitor will be current. For an inductor, it will be voltage. Cannot change discontinuously. For a capacitor, it will be voltage. For an inductor, it will be current. Energy stored is proportional to V squared for a capacitor and I squared for an inductor. When V equals 0 and I is not equals to 0, U, which is potential energy, equals 0, and for an inductor, U is maximum. When I is 0 and V is not equals to 0, the potential is maximum for a capacitor and U equals 0. So energy stored is proportional to E squared for a capacitor and B squared for an inductor. Time constant for a capacitor is given by RC, and for an inductor it will be L over R. I would highly recommend that you guys write this summary down on a piece of paper and keep it with you for the exams and the quizzes. You're going to need a bunch of these formalisms.